So this talk is going to be about reinforcement learning, as you read in the title, and specifically for a software testing task. And the reason why I chose this topic is because probably many of you by now have seen how to apply machine learning or deep learning techniques to software engineering tasks. But reinforcement learning is a bit less known in software engineering, even though there is a number of papers that is coming out every year, increasing, that use this technology. And but I thought that it could be interesting for you, since the assumptions that this technology uses are a bit different than those of, let's say, more traditional machine learning techniques, and also the building blocks that we need to define in order to solve a problem with reinforcement learning are a bit different. So that's the plan for today. I'm going to introduce, let's say, briefly how reinforcement learning works, and then I'm going to introduce, I'm going to describe the case study that we're going to apply reinforcement learning to, and I'm going to show you 3 different ways this problem can be solved, and how this, let's say, modeling part will impact the results. So this is probably, if you open a reinforcement learning book, this is the first page that you see. You see this chart, which basically tells how the agent interacts with the environment, how the agent learns. And so first of all, we divide the interaction in discrete time steps, starting from t0, time step 0. And at each time step, we receive, so the agent receives an observation. And based on that observation, it has to decide what to do, so the action AT. Then the environment computes with its own dynamics the next state, the next observation, so t plus 1, and also a scalar value, which is called the reward. And the reward tells the agent how good was that action. And the overall goal is to maximize the sum of all the scalar rewards that the agent gets from, let's say, time step 0 to the end of its life. That, let's say, in reinforcement learning language is called episode. So those are the 4 building blocks that we need to define when we want to solve a problem with reinforcement learning. The first one is the observation space. So we have to define what the agent sees during its life. Then the next step is the action space. The action space determines what the agent can do in the environment, how it can act, how it can modify the environment. And as we'll see later, the choice of the action space will actually determine the type of algorithms that we can use. Then the third ingredient is the reward function, probably the most important one. And in the reward function, we have to encode the success criterion that we need our agent to, let's say, satisfy. And the reward function will also determine the behavior of the agent once it is trained. And well, last but not least, we have also to define how an episode, or when an episode ends, since we don't have, let's say, a limited time. Okay, so prioritization. First, let me cite, let's say, the source of inspiration of this talk, which is these 2 papers. One is an ICSI paper, 2020, from Bertolino et al. And the other is actually an extension, even though it's from different authors, which is a TSC paper, 2021, from Mojtaba et al. So what I'm going to say next is based on these 2 papers, and also some my own considerations, let's say. So coming back to test case prioritization. What is it and why it is important? Well, let's say that we have a software application that we are developing, and hopefully we have a test suite that we need to run every time we make changes. And so there are two, let's say, ways we can execute this test suite. The first one is just execute all the tests. But if we have many tests and let's say they are complex, this is probably not a very effective approach since we lose a lot of time, and let's say the objective of the test suite execution is to say catch bugs as fast as possible with, let's say, a limited time budget. And the other approach is we actually devise a way to prioritize the tests based, for example, on the capability of each test to, let's say, catch a bug, or based on how fast is the test case execution. But so how do we do that? Well, usually this is solved as let's say it's formulated as a prediction problem. So we have a test case, and based on the test case itself, we decide, let's say, its rank, its priority. And in these two papers, what the authors consider is two sets of features. The first one is the execution history. So it's execution-based feature. So the first one is, for instance, verdict. So whether the test case passes or not in a certain cycle in the continuous integration, let's say, log or execution. And then we have the execution time. So how long does the test take to execute? Then we have the history of the test case across the different cycles of the CI build, and the age. Let's say how old is the test case, since how long it was introduced in the test suite, in the regression test suite. The other sets of features is code-based features, and they regard the software entities that are impacted by this specific test case. And these code-based features are divided into subcategories. So, for instance, one is program size. One example is lines of code. Then we have cyclomatic complexity, and also some object-oriented metrics, for instance, the number of class declarations. Okay. So if you think about it, this problem of prioritization can be seen as a reinforcement learning problem, since it is inherently sequential. So we have our CI build. At each time step, we receive a test case or a set of test cases, and we have to decide which rank to give to each of these test cases. The action will be the rank that we give. And then, based on this action, the CI execution environment tells us how good the action was, based, for instance, on the number of bugs that the test case catches, or how close is the rank that we give it to the optimal. But we are going to cheat. Let's say we are not actually going to execute test cases when we train the agent, and because we are going to exploit the execution logs of the previous CI cycles in order to train the agent. The authors envision, let's say, the use of reinforcement learning in production in this way. So there is the first step, which is offline, in which we train the agent from the execution logs. And once the agent is trained, then we can, let's say, apply it online. We can give it a set of test cases. The agent will rank them. We execute the regression test suite. We collect the logs. And then we can reuse these logs to adapt the agent to changes, since our code is changing and also our test suite is changing. And this, the last part that you see on the left, sorry, on your right, is what actually differentiates reinforcement learning from the other more traditional machine learning or deep learning techniques, is that it can adapt incrementally to changes, something which is more difficult to do with the other techniques. So these two parts, so train and adapt, are offline, so we don't pay too much attention to the training time, especially this first part. But this part is online, so we actually care that the prediction time of each agent is, say, compatible with the fast times of CI. Okay, so the next part is the modeling part, so how we can model this problem as a reinforcement learning problem. And well, I'm going to use one example, which is I assume that I have one cycle, and in this cycle there are 6 test cases. So the first model is called listwise, and so remember we have to define 4 things. The first one is observation space, which in this case is a matrix, where the number of rows is the maximum number of tests that we have considering all the cycles in our execution log. And the number of columns is actually the test features, so the features that each test has. Something like this. So let's say that we have 6 test cases in this cycle, but the maximum number of test cases, for instance, is 9. And so we do that because the algorithms that we're going to use are not able to handle variable size inputs. So we need to take into account the maximum, the biggest input that we can have. So in this case, we have 6 test cases. The number of rows is 9, so we have to pad the rest. The action space is discrete. We go from 1 to the maximum number of tests. And let's say that in this case, we choose the index that selects the test case number 3. And well, keep in mind that also here we can also select something which doesn't exist. So for instance, this test case here. And if we do that, well, the action is invalid. And well, when we select instead something that exists, like T3, then we update the observation space and we pad the actual place that test case occupied in the observation space. The reward function is encoded as a distance with respect to the optimal rank that we assume we have, since we have the execution logs. And is 0 if we select an action which is invalid, if we select a test case that, let's say, doesn't exist. And it's that quantity there otherwise. So let's say that the optimal rank is the one in yellow at the top, and we select T3. The first component is called the assigned rank, and it is the rank that we give to the test case number 3, which is 0, so the lowest rank, which means the highest priority. Then we consider the optimal rank, so the norm means it's normalized across the number of test cases that we have. And well, it's 0 because the numerator is 0. The optimal rank instead says, okay, the test case number 3 is at position 3. Actually, it's not at position 0. So if we normalize it, we get 0.5. And the difference between 1 and the 2 squared is that quantity there. So with the action A0, so T3, we get a reward of 0.75. And this reward goes from 0 to 1. Okay, termination condition, there are actually two. The first one is we select all the test cases. So we have no more test case to select and the episode finishes. And the second one is we run out of time. And this can happen because we can select the same test case over and over again if we get some overfitting. So we need, let's say, a safer termination condition. In the first case, so if the episode terminates, let's say, correctly, we get a sorted test suite that we can execute. In the other case, we just assume that the test cases are not ranked, and we just choose a random ranking. So pros and cons. This modeling is actually easy in a way, but the drawback is that it can have very big observation and action spaces. So if we have a test suite with many test cases, we'll have many actions and a very big observation space, which can be a problem for neural networks. The other model is called pointwise, and the observation space is actually simpler. It's just one test case with its features. Oops. The action space is continuous in this model. It goes from 0 to 1, and let's say that A0 in this case is 0.25. And what the action represents is the assigned rank that you've seen before. So the normalized assigned rank that you've seen before is the meaning of the action here. And the reward function is actually very similar. What changes is that instead of the assigned rank, in this case we have the action, since it's already normalized and it's between 0 and 1. So the optimal ranking is the one on the right. And for test case T1, we say, okay, it's position 0.25, let's say. And while instead is position 0. So we compute the difference between the two. The optimal assigned rank is 0 in this case because T1 is at position 0. And the reward is actually higher than what we had before because you're actually closer to the actual rank of the test case. The termination condition here is easier. We just have only one because we are actually presenting the agent a test case at a time. So in this case, we finish after 6 time steps. And at the end, what we have to do to have a sorted test suite is to actually take the scores that the agent assigned to each test and sort them. And so the test case is based on the score. So this modeling is easier than the previous one. It also has some other advantages like a smaller observation and action space. But we lose one of the perks that we had before, which is looking at all the test cases and deciding the rank to give to each of them. In this case, we actually score one test case at a time. We don't have, let's say, a point of reference. So this is the last modeling is let's say, something in between the two of them. Sorry, it's the observation space is twice as big as the one in the previous modeling. And so we have two test cases in this modeling, so T1 and T2. And the action is binary. It's either 0 or 1. And what the action represents is, so given these two test cases, the agent has to decide which one is more important, which one to be the highest priority or the lowest rank. If we choose one, which means T2, then we have to swap them. So T2 goes at the position that T1 had before. So the action space in this modeling acts as a comparison operator in let's say, a sorting algorithm. The authors in this case considered selection sort. And well, let's say that in this case we select T2. The reward function is a bit different than the ones we've seen before. And it is 1, so the reward scalar value is 1 if we select a test case that fails while the previous one doesn't. It also gives a score of 0.5 if instead we select a test case which is faster than the one that we don't select, and 0 points in all the other cases. So, for instance, well, this is, let's assume that T2 fails and T1 doesn't, so the reward is 1 in the next time step. The termination condition is determined by the selection algorithm, the selection sort algorithm. So when we have the 2 pointers at the end, the episode finishes. And when this condition is satisfied, then we have a test suite which is already ranked and ordered, and we can execute it. The pro of this pairwise model is that still the action space is small. The observation space is also small. Here we also, let's say, we also can compare two test cases, so we can choose between two of them. But the drawback is that the pairwise comparisons can be imperfect. So the operator, the comparison operator is not perfect. Is based on imperfect knowledge, let's say. Okay, so the last thing we're going to see is some results, and so first of all. This is how the results, let's say, were computed. We take a certain cycle. We train the agent on that cycle for 200 episodes. And then we test on the next cycle, and so on. The second time we come here, we, let's say, resume the training from the previous one. So we load the model from the previous cycle, and we actually adapt it. We don't train from scratch. What we care about is two metrics. One, which measures how close we are from the optimal ranking. And the second one is prediction time. So this first one goes from 0 to 1, and the desiderata is that it has to be as high as possible. And the prediction time is, so it has to be as low as possible, since we actually care about performance since this process is online. So regarding the first metric, we have different algorithms on the column, on the rows, sorry, and two data sets. And what we can see is that the pairwise model, so listwise, pointwise, and pairwise, the pairwise model is the one that gives the best results. This metric is close to 1, regardless of the algorithms that we use. Then the pointwise is the second best, let's say, while the listwise is the worst. And in terms of prediction time instead, in the first data set, pairwise and pointwise are actually equivalent. The prediction time is very small, while in listwise is close to a second. In the other data set, however, the best results we have with the pointwise model. And probably the reason is that there are many test cases, and with the pointwise, let's say we can rank one test case at a time instead of going through the selection sort algorithm, which for many test cases may be expensive. So to wrap up, considering all the modeling, all the ways, let's say, this problem can be modeled, and the two metrics, so say ranking performance and prediction time, we have that listwise is the worst of the three in both metrics. While pointwise and pairwise, there is a, let's say, a trade-off between performance, ranking performance, and prediction time. So let's say these results show you that the way a certain problem is modeled, is formulated, actually has a huge impact on the results. So this actually concludes my presentation.